Hello, today's topic is longest common substring problem. I'll be presenting today. This course is for the presentation 2 for the course COT 5405, Design and Analysis of Algorithms. So let's start today's topic. The roadmap for today's presentation will be, first of all, we'll define the problem statement, that is the LCS, longest common substring problem. Then we will look at a data structure called Trie, and then we will introduce suffix trees. Then we will see Ukkonen's algorithm, which helps us to construct suffix tree in linear time. Then we'll learn about suffix arrays and longest common prefix LCP array. Then we'll see how to construct suffix array and LCP array. And then finally, we'll solve our problem statement LCS using suffix arrays and LCP array by giving an example. So the problem statement, LCS problem statement, simply states that given two strings X and Y of total length n over a constant sized alphabet, so that we can compute the longest common substring in O of n time. So let's assume like we have two strings, X equals to A, B, C, D, and we have Y equals to B, C, D, E. Then we can see that common is BCD, so the output will be BCD is the longest common substring. So our target is to compute in O of n time. So our normal approach that we can apply is through dynamic programming. So if we use dynamic programming, we can solve this problem in O of n squared times the complexity. So today we'll be looking at a new data structure called Trie, and suffix tree will be using suffix tree to solve this problem in linear time. Now let's move up to the next part. So let's get introduced with a new data structure that we are gonna be using for this problem. It's called Trie data structure. So a Trie data structure is nothing but simply a tree structure where nodes represents one character and the root represents the null string. The basic advantage of using this Trie data structure is that the lookup is faster, even in the worst case scenario. The lookup can be done in O of m time complexity, where m is the length of a search string. The another advantage that Trie provides is that it provides an alphabetical ordering in the entries by key. So in total, what we can say about Trie data structure is that it is a type of tree. Often we use this to store characters. Each node might store a character as its data, but then if you look at a path from the root down to that node would be really representing a part of the string or the complete string. So let's see an example. So let's assume we have S1 equals to A, B, C, S2 equals to A, B, D, and S3 equals to B, B, C. And a normal, how we can construct a tree data structure is that will be, this is our root. We will extend to A, B, C. Then for S2, we'll follow the same path, A, B, and since we need a D, so we'll make a new D here. And for S3, since S3 starts from B, so we have to make a new child here, B, and C. So this is how we can construct a normal tree data structure. After this, let's move. Now we'll be utilizing the concept of this Trie data structure to build a suffix tree, which is the main topic for our discussion today. So let's go to the suffix tree. So suffix tree introduction. So basically, if we are introducing a suffix tree, suffix tree. Suffix tree in general, the normal definition of a suffix tree will be is a compressed tree of n strings that are suffixes of an n character strings. And it helps in constructing the suffix array in linear time and can be stored in linear space. So the basic things that we can conclude from this and we can acknowledge from suffix tree is that it will ensure that every suffix ends at terminal node and will append a sentinel character to the end of each leaf of the suffix tree. It also helps in avoiding redundancy when representing strings, because the strings with common substrings, they are represented only once. So it is very useful in this modern string operations like exact pattern matching, finding substrings, longest palindrome, DNA contamination, suffix arrays, longest common substring, etc. Today's our topic will be using suffix tree to solve the longest common substring problem. A normal brute force approach for construction of a suffix tree would be we'll be considering all the suffixes of a given string as a separate string, and then we'll insert them in the trie one by one. This will yield us a time complexity of O of n square, which is not our required target. So the target for our solution today is to solve it in O of n times. So let's get more knowledge about the suffix tree. So while building a suffix tree, we have first step is to build a trie. From trie, we'll go to a certain step called implicit suffix tree. We might come up with this, and from implicit suffix tree, we can build a full suffix tree. So we have to understand what is an implicit suffix tree. An implicit suffix tree is that tree which can have at most n leaves, whereas the normal trie will have exactly n leaves. And the basic thing, how can we eliminate this implicit suffix tree so that we can obtain a suffix tree, is by we'll append a special character which is not equal to any other character of the string, which means that it should be lexicographically smaller. The character that we append should be lexicographically smaller than the characters which are present in our input string, which means basically the ASCII values should be less than from these values. So let's see an example to understand. So let's consider our string as banana. So if a banana is string, so our implicit suffix tree will be as shown in the figure, ANANA, then we have banana, then we have NANA. And to build a suffix tree for the string banana, we'll append a $sign at the end of the string, and then we'll build the equivalent suffix tree for the input string. We'll talk about how to construct this suffix tree in the next slide. So Ukkonen's algorithm. Ukkonen's suffix tree construction algorithms takes O of n time and space to build suffix tree for a string of length n, and after that, when we perform the traversal of tree, it will take O of n time to build suffix array. So overall it is linear in terms of time and space. That's why it provides us with a linear time construction algorithm, and that is what our today's target is, to build a suffix tree in linear time O of n time, so that we can perform our LCS operation, longest common substring operation, in O of n time. So a basic question is like, why is the traversal O of n time? We'll talk about that when we'll talk about this suffix array. So we'll talk about that in that topic. Let's continue with our Ukkonen's algorithm topic. So as I said, it helps us in constructing a suffix tree in linear time. In the worst case scenario, It effectively utilizes the storage and reduces space complexity. So the basic formulation of the suffix tree. Ukkonen's algorithms for construction of a suffix tree is as follows. So it divides, the first thing is that Ukkonen's algorithms divides the process of constructing suffix tree into phases, and each phase is further divided into extension. So let's suppose in the ith phase, ith character is introduced in the trie. Then in the ith phase, all the suffixes of the string s extending from, if the index is, let's suppose the index start as 1. So all the suffixes of the string s from 1 to I are inserted into the trie, and inserting j suffix in a phase, it will be called as j extension of the phase. So in the ith phase, there are I extensions, and overall there are n such phases, where n is the length of a given string. So this gives us a hint that right now it's not a O of n square, O of n time algorithm. It looks equivalent to like O of n square time algorithm. So, but the algorithms will, this algorithm, Ukkonen's algorithms, express this fact that there are suffixes of the same string and introduces several tricks to bring down the complexity to O of n. So now the basic thing is like how to perform the extension phase. So to perform the jth extension of the ith phase, in the jth extension of the ith phase, the string s, j to I is to be inserted. So before going for phase I minus 1 phases are already complete, that we know. That means that we will have a trie having all suffixes of strings from 1 to I minus 1. So the search for the path of the string s, j to I minus 1 in the trie will have 3 possibilities. And these are the 3 extension rules that we apply for constructing a suffix tree while using Ukkonen's algorithm. So the first rule says that if the complete string is found and the path ends at the leaf node, then the ith character is appended to the last edge level and no new node will be created. The second rule says that if complete string is found and path ends in between an edge level and the next character of edge level is not equal to si, or the path ends at an internal node. In this case, new nodes are created. So if the path ends in between an edge level, then a new internal node and a new leaf node is created. Whereas if the path ends at an internal node, then a new leaf node is created. Rule number 3 says that if complete suffix, that is s, j to I minus 1, is found and the path ends in between an edge level and the next character of that edge level is equal to the ith character, in this case, we'll perform nothing, we'll do nothing. So using those 3 extension rules, we perform extensions in a phase. So a basic thing that we can look or we can see at this phase is that we are doing n phases, and for all the ith phase, we are performing I extension. So for every extensions, we need to find the path of a string s, j to I in the trie built in previous phases. So if we go with brute force approach time complexity, this will yield us a very worst time complexity of O of n cube. So now we do certain speed ups in this Ukkonen's algorithm, or certain techniques we apply to bring down the complexity to of O of n. So a normal, like 3 speed ups that we applied is that we use the concept of index pairs. We use the concept of suffix links, and we even can use 3 tuple to represent the things. So the basic things that we are going to discuss now is to bring the speed up in the Ukkonen's algorithm so that we can build a tree, build a suffix tree in linear time. So let's first talk about what is a suffix link. So normal definition. So like let's assume a string G is present in the tree and its path from the root ends at a node V. Also, there is a string alpha G in which is present, and where alpha might be any character, and its path from the root ends at node W. Then a link from W to V will be termed as a suffix link. So the question arises, how does suffix link help? The basic criteria is that when we are performing the Z extension for the phase I, we are looking for the end path of the string S for J to I minus 1. And in the next phase, we'll look for end part of the string S J plus 1 to I minus 1. But before coming to phase I, we know that we have already performed I minus 1 phases. That means we have already inserted strings S J to I minus 1 and S J plus 1 to I minus 1 in the trie. Now clearly we can see that we don't have to go all the way to the root to find and to again research the tree. So we can utilize this suffix link. So we can use a suffix link from node at ending path to node at ending path as J plus 1 to I minus 1. So instead of traversing from the J plus 1 extension of the ith phase, we can make use of the suffix link and traverse from there onwards. So ultimately, the use of suffix links makes the processing of a phase of number of nodes in the process. And the number of nodes in the compressed tree is O of n. So each phase will be done in O of n, and there are n such phases. So suffix links will help us to complete and help us to reduce the complexity to O of n squared. So the second thing that can bring up issue in our suffix tree is that the edge levels. So right now on our edge levels, we are using all these strings as the edge levels. So if the edge levels will be stored as strings, the space complexity will be turned out to be O of n squared, no matter what the number of nodes or strings we take. So for that, the basic criterion is we use the index pairs as edge levels, where the two variables will denote the start index and the end index of a level in the string respectively. So in this way, each level will take constant space and will have a complex space complexity will be O of n. In addition to that, furthermore, we can use the three tuples to represent the active node, active edge, and number of repetitions in the suffix tree implicitly. For example, let's see if we say like this root, and then let's say a string and then 2. This means that our active node is at root, active edge is A, and then the number of times A is repeated is twice in the thing. So now summarizing this algorithm. So in any phase, the extension rules will be applied in order. In first few extensions, rule 1 is applied. In the next few extension, rule 2 is applied, and in the next rule 3 will be applied. So the thing is that we have to keep in mind is that if we apply rule 3 at phase I in extension J for the first time, then the remaining extensions will be applying the same rule. We won't be switching back to rule 2 or rule 1. And only rule 2 is where we create a new leaf node. A new leaf node created will always remain a leaf node. Only the edge level of the edge between itself and its parent will keep on increasing because of application of rule number 1. New leaf nodes will be created when rule 2 is applied, and in all the extensions which rule 2 is applied for any phase I minus 1, in the next phase I, rule 1 will be applied in all those extensions. So maximum n times rule 2 will be applied, and in all these extensions, and we have n leaves. So this means that we can complete all the phases. All the phases can be completed in complexity of O of n. Since we have a maximum of n times, we are applying rule 2, and there are n leaves. So all the phases can be completed in complexity of O of n. So a basic how we're gonna do the LCS problem using suffix tree. The basic thing is like we have an input string x and y. Output will be a longest common substring. So first thing is that we will be appending a sentinel character, which is logically, graphically smaller than the input strings. So let's say we have input string x and y, then we'll construct a suffix tree for x has y dollar. This is, we concatenated the two strings, then we'll find the deepest internal node containing both x and y leaves, and whichever will be the deepest internal node containing the length, that will give us the longest common substring. Time complexity will be O of n plus size of the size of the input string, which we can equivalently say it's O of n time. So if we see a normal example like how to construct a suffix tree with all those Ukkonen's algorithm and all that we learned above, then let's assume we have s equals to a b a dollar. Then we'll have a root for dollar sign. Then we have a dollar. Then we'll have a dollar, and in this one, then we'll have a b a dollar. We'll have a b a dollar. Give us the whole string. And then we'll have, so b is different, so we'll have a new for b a. Then we'll have b a dollar. Then we'll have b a dollar. So we have a suffix tree using the Ukkonen's algorithm. All we have to do, so we will build a similar suffix tree for the concatenations. Let's suppose T is the concatenation, so T will be x has y dollar. We will be building a suffix tree for this, and then we'll be comparing, and whatever deepest internal node containing x and y, that will be the longest common substring. That will be our required solution. So let's go to some other thing. Now, the concept of suffix arrays and LCP arrays. So suffix arrays, suffix tree can be created in O of n time and O of n space using suffix arrays and longest common prefix LCP arrays. So what is a suffix array? So the prime motivation for using suffix arrays is to note down all the suffixes, sort them lexically, and store their index positions in the array. And the resulting array, what we receive, is the suffix array. And the principal idea for the LCP array is to compare the adjacent elements in the suffix array and compute the length of their longest common prefix. The length of the LCP is stored in an array. So if we have a suffix array of the string, then to get its suffix array, we just need to do a lexicographic order, which means alphabetical order, DFS traversal, and store all the suffix indices in resulting suffix array. So the principal thing is like why the traversal, like I said, why the traversal is O of n time. Because once we have build a suffix tree for a string of length n in O of n time using Ukkonen's algorithm, we can traverse the tree in such a way that it will take O of n time only to build suffix array. The prime reason for the traversal to take O of n time is because a suffix tree of length n, because a suffix tree of length n will have at most n minus 1 internal nodes and at most n leaves. So by this, we can say that the traversal can be done in O of n time. So once we know the concept of suffix arrays and what is a suffix array, what is LCP array. So now we will see how to construct a suffix array and LCP array. So the prime thing in the suffix arrays and LCP array construction is that first thing is we have to build a suffix tree. Okay, so let's consider our example string. Let's consider it as a banana. So banana, and we appended a $sign at the last to the string so that we won't be getting an implicit suffix tree. To remove that implicit suffix, we have appended a $sign. And let's call the indices start from 0. So 0, 1, 2, 3, 4, 5, 6 are the respective indices. Now we are will receive the following suffix tree for this string. So we have this one is our root. So so 6. This is 6, so this leads us to $. Let's start from 0. So banana. So 0. So this root will lead us to whole string banana $0. 1 is ANA. So we'll traverse this tree ANA $. So this is our index. So we reach here with the suffix tree ANA $. And NA $. So with this we reach here ANA $, $. And we have NA $, we reach here, ANA $, we reach there. Now we have $, and then we have $. So this is our suffix tree. Once we have a suffix tree, we will perform ordered suffixes. We'll obtain our ordered suffixes, means like we'll sort the suffix array lexicographically. Lexicographically means alphabetically. So this is what we obtain. So once we get all the suffixes here from our suffix tree, then we will order the suffix tree. So the first one comes at $, then we have $, then we have ANA $, then we have ANA $, BNN $, NA $, and NNA $. So these are the suffixes of the string banana $. So if you see, these are sorted lexicographically. We have sorted according to alphabet A, B, N, and we will not be storing this one. This one will not be storing. We'll be storing this as a suffix array. Suffix array. This one is our suffix array. The suffix array will be storing the index value. So for $, index value is 6. So suffix array will be stored 6. Similarly for $, it will be storing 5. Banana $, the index value is 0, so it will be storing 0. So this is our suffix array. So once we have a suffix array, we will get an LCP array. How to get the LCP array? The LCP arrays can be obtained by looking at the adjacent elements in the suffix array, and we will get the length of their longest common prefix, which on storing the length will give us the LCP array. The LCP array is like an auxiliary array that we use to help us with more refined result. So let's compare the two adjacent elements in the suffix array. On comparison of 6 and 5, we see there is nothing common, so it will yield 0. On comparison of 5 and 3 in the suffix index, we see that A and A is common, so it will have one value of 1. On comparison of A and A, 3 and 1, we'll see we have common is 3. 3 strings are common. So, and comparison of A and B, when we compare 1 and 0, we have 0. When we compare 0 and 4, we don't have any common. When we compare 4 and 2, we have compared 2. So this is the array that we have received here. This is our LCP array. The main advantage of the LCP array is what? What do we get by getting an LCP array? LCP array is clearly giving us the value of what is the common between the suffixes. So let's see, here we have the value 3, highest, right? And here we have 0, means there is no matching here. We have 3 here, 0, there is NA and NA is matching here. So this is how we construct a suffix array and the LCP array. Now we will use this concept of suffix array and LCP array to solve our problem, LCS problem. So the LCS problem, longest common substring problem. So let's assume X equals to ABCA and Y equals to BCAD. So to find the LCS, first we have to create a new larger string T, which will be the concatenation of the strings X and Y separated by unique sentinels. And the sentinels that we will be choosing should be unique and lexicographically less than any of the characters that are contained in the input string, which basically means that the ASCII value should be lesser than A to AZ to Z. A to Z, A to Z. So then we'll come to this step. So our string T will contain X plus S sign as one of our sentinel character, and dollar sign is another sentinel character for our case. So T equals to X plus this will give, and the concatenated string will obtain is ABCA has BCAD dollar. Then we'll be constructing a suffix tree. We'll build a suffix tree for this string. We'll build a suffix tree for the string T. From suffix tree, we'll build a suffix array. And we already know from now that we can accomplish the construction of suffix array in linear time with a linear suffix array construction algorithm. And then in addition to constructing a suffix array, we'll construct a LCP array from the suffix array. And then we can easily get the longest common subsequence between X and Y on comparison. So let's see the example on how to get an LCS. So see, as we saw in the last slide, we have assumed our X to be ABCA and Y to be BCAD. And the two sentinel characters that we assumed are S sign and a dollar sign. Then the T will be the concatenation of X and Y with these sentinel characters, X plus this plus Y plus this. And our corresponding T that we obtain will be ABCA has BCAD dollar. So now let's let's be the indexes start from 0. So the indexes for that corresponding to A is 0, B is 1, C is 2, A is 3, for hash 4, 5, 6, 7, 8, and for $9, the index is 9. So now the first step is we are to be building a suffix tree. So on building a suffix tree, we'll be obtaining these suffixes. the next step is what we do is that we will order the suffixes lexicographically, means we'll be sorting the suffixes on for this string. On building a suffix tree, we'll obtain these following suffixes, and on ordering them lexicographically, this is what we obtain for the responding. And we are already know that we are not going to be storing this as an R suffix array, but we'll be storing the corresponding indices as the suffix array. So we can see here hashtag BCAD dollar. So the index is 4. That's why we're storing 4. For dollar, the index is 9. That's why we're storing 9. For a hash BCAD, the index is 3. From here, this is the component that we're storing this. If you see this one, the BC a hash, so the index is 1. That's why we're storing 1. And correspondingly, we can see that for D dollar, the index is 8. That is the index is 8. So this is our suffix array. Once you have constructed the suffix array, then we'll be constructing LCP array. And we already know how to construct an LCP array. The basic idea to construct LCP array is to look at the adjacent elements in the suffix array and get the length of their longest common prefix. Longest common prefix. So this I already know will have nothing. On comparison, this will get nothing. In comparison with this, nothing common. So now on comparing 3 and 0. Index 3 and index 0, we see they have AA as common, so 1. On comparison of 0 and 7, we have AA is common, so we get result 1. On comparison 7 and 1, A and B starts with A and B, so there is nothing common between them, so the value will be 0. In comparison of 1 and 5, BCA, this we can see that BCA and BCA is common, so the LCP array will contain the value 3. In comparison of 5 and 2, we see this starts from B and C, so we'll get 0. On comparison of 2 and 6, you can see this is will get a common as CA, so we are getting value of 0. Comparison of 6 and 8 index, we see these are different, so we value of 0. Now we can see how many common things are there in between our X and Y. So on traversing the LCP array, we can see the highest value is obtained is 3. So which is our required answer is BCA is the required longest common substring between X and Y. In this way, we can employ suffix array and LCP array to find the LCS. So that's it for the presentation today. I hope you guys have a good day.